Beneath the world's oceans lies a mineral frontier: copper, cobalt, nickel, zinc, silver, gold, and rare earth elements essential to clean energy and high tech. As nations pursue net zero goals, demand for nickel, cobalt, and rare earths is projected to roughly double by 2040. These metals power EV batteries, wind turbines, electronics, and advanced defense systems. With finite or concentrated supplies on land, attention is turning offshore, to the abyssal seabed. The Clarion-Clipperton Zone, or CCZ, may hold several times the cobalt and nickel found on land. Supply chains are vulnerable. China controls most rare earth supply and battery production, creating geopolitical leverage. Japan, highly dependent on rare earths, is testing deep-sea extraction to diversify. Advocates say undersea minerals can secure materials for the 21st century economy. In this film, we explore how deep-sea mining works, the resources, the science, the risks, the economics, and the geopolitics. We begin with what lies in the deep, and how miners aim to reach it. This is Earth's largest habitat, kilometers below the surface, cold, high pressure, and largely unknown. Deep-sea mining refers to extracting minerals from the ocean floor, often 4 to 6 kilometers down. Technology is racing ahead. The question is, should we follow? First, a closer look at the resources drawing industry to the deep. The seabed hosts 3 main types of deposits, and each demands a different approach. Polymetallic nodules, potato-sized rocks, litter abyssal plains at 4,000 to 6,000 meters. They accrete over millions of years and are rich in manganese, nickel, cobalt, and copper. The CCZ alone may host over 21 billion tons of nodules, an immense cache of battery metals. Because they lie on the surface, nodules are the simplest to collect, at least in theory. Polymetallic sulfides form at hydrothermal vents as mineral-rich fluids cool and precipitate. These mounds can contain high grades of copper, zinc, silver, and gold. They occur along volcanic ridges and basins, sometimes inside national waters. Cobalt-rich crusts coat seamount flanks and summits, forming hard layers over millions of years. These crusts can be centimeters thick and are valued for cobalt, manganese, and nickel. Countries like Japan and Korea have mapped promising crust zones within their EEZs. Nickel and cobalt feed EV cathodes. Rare earths power high-strength magnets for wind turbines and motors. Strategic metals underpin aerospace and defense capabilities. Under net zero scenarios, demand trajectories steepen, driving interest in new sources. But geology is only the beginning. The challenge is getting them to the surface. Next, the engineering of deep-sea mining. For nodules, think underwater vacuum, a surface vessel, a 5-kilometer riser, and a heavy robotic collector. The crawler suctions nodules and sediment, sending slurry up the riser to the ship. Powerful pumps maintain flow under crushing pressure and near freezing temperatures. On board, initial separation occurs. Tailings are planned for discharge at depth to limit surface plumes. At hydrothermal vents, cutting and dredging tools fragment ore for pumping to the surface. Crust mining requires rock shaving on steep terrain, an experimental and delicate task. Dynamic positioning keeps a 250-ton pipe vertical in rough seas while operations continue. Tethered and autonomous systems must work reliably far beyond human reach. Engineering margins are slim. High pressures, fatigue loads, and abrasive slurries push materials to limits. In 2022, a pilot in the CCZ lifted thousands of tons of nodules to the surface, first at scale since 1970s tests. In 2021, a 25-ton harvester trial suffered a detachment incident, later recovered, highlighting real risks. Independent scientists now shadow trials to measure plumes and disturbance in real time. Japan successfully test-mined a hydrothermal deposit and is probing rare earth-rich mud at greater depths. commercial reliability remains unproven. Systems work, but can they work continuously and profitably? That brings us to the ecological stakes. The deep ocean is not barren. Thousands of species live on or around the very deposits targeted for mining. Nodules provide hard substrate in a soft sediment world. Remove them, remove habitat. Vent ecosystems are uniquely adapted to mineral-rich chemistry and are highly localized. Collectors crush and bury organisms in their path. Sessile life likely dies on contact. Where nodules are removed, endemic species lose habitat that took millions of years to form. Sediment can clog feeding structures and gills beyond the mined area. Past experiments show tracks visible decades later. Ecological functions remain depressed. Microbial loops and carbon cycling can be reduced long after disturbance. Commercial projects could cumulatively alter regions for generations. Vehicles and return water create plumes that may travel kilometers, spreading impacts. Studies show fish avoiding plume-affected areas. Scavengers decline near disturbance sites. Continuous mechanical noise and bright lights intrude into a world evolved for darkness and quiet. Disruptions to sediments and biota may weaken carbon sequestration in the deep. Many scientists advocate a precautionary pause until safeguards and knowledge catch up. Environmental stakes feed directly into costs and risks. Up next, the business case. Seabed minerals are often valued in the trillions on paper. Ore grades can be compelling versus land ores. A ton of CCZ nodules can yield a rich mix of nickel, cobalt, and copper. Optimized scenarios point to healthy margins, if technology, prices, and permitting align. But capital needs are vast: ships, collectors, risers, processing, surveys, and monitoring. A price dip or cost overrun can erase profits. Legal and mitigation costs add drag. If multiple projects launch, oversupply could depress prices and compress margins. 30-plus exploration contracts span the Pacific, Indian, and Atlantic. State-backed and private actors are involved. Prominent ventures have piloted nodule collection and now seek exploitation pathways and financing. European efforts pair engineering with independent scientific observation. New entrants from offshore-savvy nations eye 2030 as a possible start line. High-profile failures like Nautilus show how technical, financial, and social risks can sink ventures. Some downstream buyers pledge not to use seabed minerals yet, signaling market hesitation. Investors weigh potential windfalls against ESG risks and regulatory uncertainty. Ultimately, policy will shape the runway. Let's go there next. Who governs the deep and on whose behalf? International waters are governed by the International Seabed Authority under UNCLOS. Seabed minerals beyond national jurisdiction are deemed the common heritage of humankind. A mining code to govern exploitation remains under negotiation, with missed deadlines and unresolved standards. A 2021 trigger accelerated talks, but states chose not to rush incomplete rules. No commercial licenses have been issued. Many ISA members affirmed that mining should not proceed absent agreed regulations. A growing bloc, European states, Pacific nations, and others, supports a moratorium or precautionary pause. France banned deep-sea mining in its waters and advocates an international ban. Regional bodies echo public concern, urging restraint. Sponsoring states reliant on future royalties push for progress to capture development benefits. Some firms explore alternative legal routes outside ISA frameworks, testing the regime. Contentious issues include environmental thresholds, liability, and fair benefit sharing. Talks continue, with transparency and science integration as priorities for 2026 sessions. Regulation will define pace and standards, but science will define what's acceptable. Let's examine what field studies are finding about impacts in detail. From plumes to predators, the web of effects is complex. Seafloor collectors generate near-bottom plumes. Return water releases can create midwater clouds. Models and measurements show plumes traveling kilometers, affecting areas beyond the mine site. Suspended particles may carry metals, alter chemistry, and reduce water clarity. Field tests report fish and shrimp avoiding plume zones. Predators and scavengers decline near disturbances. Concerns extend to pelagic spawning grounds if plumes enter open ocean habitats. Midwater communities, key to food webs, may be sensitive to chronic turbidity and chemistry shifts. Operations project continuous noise through the water column, potentially stressing deep-diving mammals. Navigation, foraging, and communication can be disrupted over large areas. Bright lights and perpetual darkness may alter behavior and reproduction cycles. Mitigations include gentler collectors, plume filtration, and optimized discharge depths. No mining areas can serve as references and potential sources for recolonization. Continuous monitoring and adaptive management are being built into trials. Yet, many argue unknowns remain too great to proceed at scale. Meanwhile, metal demand keeps rising. Are alternatives viable? Recycling and substitution can help, but timelines and volumes may fall short in the near term. Japan targets rare earth-rich mud near Minamotori at 6,000 meters to reduce import dependence. Trials assess extraction feasibility and plume impacts from mud lifting. Earlier, Japan cut and lifted zinc-rich ore from a hydrothermal deposit, a world first. European programs pair industry pilots with multi-institute studies to quantify sediment and biological effects. Data from trials informs models and draft regulations. Public scrutiny and ESG standards shape corporate positions and funding. Pacific nations weigh potential royalties against cultural connection to the ocean and fisheries risks. Food security and ocean health are front and center in regional debates. Many have called for a pause, citing the need for science and inclusive decision-making. Firms pivot to phased pilots, stronger baselines, and stakeholder engagement. Operational culture adapts around precaution and transparency. If allowed, first movers will aim to integrate quickly into battery supply chains. But the deep sea does not forgive haste. Robust baselines are the bedrock of any acceptable plan. Next, scenarios for the coming decade. A narrow path. Limited regulated pilots with strict thresholds, third-party monitoring, and staged scaling. Operations pause automatically when environmental triggers are crossed. Transparency, data shared openly, builds or erodes social license based on outcomes. A broader pause drives investment into recycling, substitution, and land supply diversification. Urban mining and cathode-to-cathode recycling expand, narrowing virgin metal demand. Chemistry shifts reduce reliance on cobalt and nickel in some segments. Legal fragmentation could emerge if actors proceed outside multilateral rules, raising conflict and liability risks. Risk pricing climbs. Financing and offtakes become harder without clear governance. Corporate commitments and consumer perception may constrain adoption of seabed metals. Three levers shape outcomes: robust science, enforceable standards, and genuine stewardship. Inclusive processes can align security of supply with protection of the global commons. The choice is not growth or nature. It is how to balance both without irreversible loss. If seabed metals proceed, downstream traceability and standards will be pivotal. Traceable, audited supply chains could be a condition for market acceptance. Let's close with key insights and open questions. 3 deposit types promise critical metals. Technology has advanced to credible pilots. Integrated systems can lift ore, but reliability, costs, and impacts remain pivotal unknowns. Ecological risks are profound, especially habitat loss and long recovery times. Plumes and noise may affect midwater life and fisheries far from the mine site. Social license depends on transparent science and inclusive decision-making. Profitability is highly sensitive to prices, costs, and regulatory delays. Global rules and moratoria will determine if, when, and how mining proceeds. Recycling and substitution can blunt demand, but likely not fully replace virgin supply soon. Watch for 2026 ISA negotiations, Japan's trial results, and independently reviewed environmental data. Track OEM sourcing policies. These will shape market demand for seabed metals. Expect more transparent monitoring and public dashboards around any pilot operations. The deep sea is a shared heritage. Choices made now echo for centuries. If mining proceeds, it must do so under rigorous science, enforceable standards, and real accountability. Thank you for watching. Explore the sources and continue the discussion below. A 2022 CCZ pilot retrieved thousands of tons, validating lift and handling at depth. Monitoring suites logged plume behavior and benthic impacts for post-trial analysis. Metallurgical pilots convert nodules into battery-grade intermediates. A detachment left the crawler on the seafloor before recovery, illustrating operational hazards. Independent teams collected impact data, setting a template for future pilots. Incidents fuel calls for stronger safeguards, or a pause. A 2023-2024 analysis found fish avoided zones beyond visible deposition, likely due to plume effects. Mobile predators showed reduced abundance for at least a year in the test area. Learnings informed design tweaks to minimize contact and resuspension. Engineering feasibility is rising. Environmental acceptability remains the gating factor. Future pilots will be judged on transparency, independent science, and adherence to limits. The deep remains largely uncharted. Humility is warranted. Appendix materials and links are available in the description. End of appendix. What if the metals for our clean energy future lie 4 kilometers down, on a habitat that took eons to grow? Do we mine the deep to decarbonize, or protect the deep to preserve life? Between pilots and pauses, the next decade will decide. Deep sea mining for rare earth minerals and strategic metals. Follow the Elemental Science Magazine channel for more deep dives on climate, policy, and critical minerals.